All right, so good morning. Welcome to another fun-filled day of calculus. Our plan today, of course, after going over any homework questions, is to keep looking at the fundamental theorem of calculus. We're going to practice a little bit with the form that we saw that basically lets us do these definite integrals quickly, right? And then I'll show you the other form, which is kind of the magic behind calculus, really, and why the fundamental theorem gets its name. And then we'll just keep plodding along. All right, so that's kind of our goal for today. But before I take off and start running, are there any homework questions you guys would like to look at, or any questions on what we've been talking about so far? All right, so Susanna's requesting number 16 from 1.3. Right, and then Juan's following that up with number 3 from the same set. All right, so it looks like we've got those two. Let's go take, and then number 6 just got thrown on there as well. So let's go take a look at those guys. Now it is possible, because these are from the Fundamental Theorem of Calculus section, that we might not have talked about the portion necessary to do all of these yet, but we'll just sort of see. So I'm going to go ahead and share my screen here. And we'll go take a look at these guys. All right, so question number 3. Let's go take a peek at that one first. All right, this is one we haven't talked about yet. So I'm going to hold off on looking at this one just yet. We'll do it later. Let me go ahead and write it down just so that I know what we're trying to do here. Because as of right now, you have no clue how to even start doing this. There's definitely a fast way, and that will be the Fundamental Theorem of Calculus, the other part. Remember, I told you I did the parts out of order. So I actually did part 2 first. So we'll do part 1 today, and then this will make more sense. So we'll come back to this one, whoever asked for number 3. Let's take a look at number 6. All right, same story, actually. This is also from the quote-unquote first part of the Fundamental Theorem of Calculus, but I'm going to go ahead and write this down as well so we can talk about it when we get there. So then let's take a look at the last one that people asked for, was number 16. All right, this one we can do. This one we can definitely do. All right, so this one's asking us to find the blue shaded area. It says we're going to calculate this integral. And basically what it's asking us to do is figure out a and b, so what the bounds on the integral should be, the function that we're integrating, and then lastly, what the actual area is. All right, so let's start with the lower and upper bounds. How do you figure out what the lower and upper bounds are here? Or what would they be? What's A and what's B? All right, so we got a couple of people chiming in. Mariola said 1 and 2, and Juan Carlos said A equals 1. So yeah, this one we are going to go from 1 to 2. So if you look at it, basically just look at the graph and like what's the leftmost portion of this region, what's the rightmost portion, and those are our bounds. So this is going to be from 1 to 2. So then we need to get the function. And so the function is just going to be this top. It definitely looks like a line to me in terms of what its equation is. Look for nice points. So looks like we've got a nice point right here, nice point right there, nice point right there. So it looks like this has a slope of -1/2. Right? Good old rise over run. I'm dropping 1 as I go over 2. So -1/2. Looks like it's got a y-intercept of 5. So let's put in -1/2 x plus 5. Syntax error. Nope, we're good. All right. And so then lastly, the question is, what is the area? Well, this one, we could do the integral. We could actually anti-differentiate and put in the values. I'm actually going to cheat a little bit. Let me come back up here. So this one, the area, since it's geometric, I could actually calculate it. I've got a little triangle on top of a rectangle, right? The rectangle is 1/4. So that's got an area of 4. And then this triangle, its area is 1/2 base times height. Its base is 1, its height is 1/2. So 1/2 times 1 is 1/2. Half of that is 1/4. So I've got 4 1/4. And hopefully I do this math right. That area is 17/4. All right, so that's what it looks like just geometrically. Now you might go, well, that's all great if we've got a line and then we've got a nice little shape like that. So let me show you how we could have done this using the fundamental theorem. So let me share my whiteboard here. All right, so what we were doing is we were integrating from 1 to 2, and the function was -1/2 x plus 5. All right, so this is actually the notation that would describe exactly that picture. So remember what we saw from the Fundamental Theorem of Calculus? Let me actually run that over here. From the Fundamental Theorem of Calculus, excuse me, says that if we integrate from a to b, f of x dx, that's going to equal big F of b minus big F of a, where big F is an antiderivative. All right, so all we have to do is find an antiderivative of this thing that's in the integral. So let's do that over here with this function. So let's go back to what we learned about antiderivatives. When you have constant multiples, those things just stick around. So the -1/2 is going to stay -1/2. And then we've got x to the first. So we're going to use the power rule. And the power rule for anti-differentiation says add 1 to the exponent. So we're going to get x squared and then divide by that exponent. So the -1/2 x is going to give us -1/2 times x squared over 2. And then the 5, that its antiderivative was just 5x. Anytime you had a constant, the antiderivative is just that times x. All right, so then we're going to remember that we're actually going to apply the fundamental theorem, so I'll use this notation. So now we just plug in 2 and we plug in 1 and subtract them, right? We just do what's over here. So this is going to be -1/4 times 2 squared plus 5 times 2. And then we're going to subtract from that -1/2 or 1/4 times 1 squared plus 5 times 1. All right, so 2 squared is 4 times -1/4 is -1, plus 10 is 9, so that was 9. Over here, we're going to get 5 minus 1/4, so that's 19/4. if we get a common denominator, 36 minus 19, I believe is 17/4. And so the fundamental theorem of calculus says that this area should be 17/4. So even if you don't have something nice geometrically, like this was a nice shape, but it was because it was a line. But even if you don't, all you have to do is get an antiderivative and you're good to go. All right, so let me go back, make sure we answered everything on that question. Pretty sure we did. So we've got our bounds from 1 to 2, our function, our area was 17/4. And yep, there it is. So I'm going to go ahead and submit the question because I like getting points. Yay, 10 out of 10. All right, so in general, that's the process. Anytime you want to find an integral, we've now got a fast way. We got the fundamental theorem of calculus. So for whomever asked for 16, does that look good? All right, anything else from the homeworks that we want to look at before we kind of get back to doing these integrals? No? Okay, cool. Well, then I'm going to switch over to the whiteboard. So I will see you guys in just 1 second. All right, so fundamental theorem of calculus, as you just saw with that homework problem, can be really, really useful and really, really helpful. So I just want to show you a couple more examples so we can kind of get the feel for how it's done. And then I'll show you the other portion of the fundamental theorem, which will allow us to do those other homework questions that a couple of you asked about. All right, so the key to all of this is being able to get antiderivatives. So it's going to be really important that you go back and you practice those. And really, it's nothing new, right? Antiderivatives, no new rules. It's the same rules as differentiation. You're just going backwards. So we have to think about, instead of going from left to right, we're going from right to left. So that's one good thing, is that it's not new. But you do have to train your brain to think backwards, because up to this point, you're probably really comfortable with doing derivatives and you just differentiate, differentiate, differentiate. We now have to think about, whoa, we've got to go the other direction. All right, so some more examples of the fundamental theorem, right, just for some practice. So let's get away from polynomials. We've been doing all kinds of stuff with polynomials. Those are pretty easy. Let's change functions around. Let's look at, say, the integral from 1 to 2 of 1 over x dx. So hopefully you all know what this function looks like. That's just a good old butterfly function. For those of you who don't know me, I have all kinds of weird names for all kinds of functions. This one I call the butterfly function. You can see that pretty easily if I draw the picture of it. There are axes. 1 over x looks like this. And if you don't see why I call this the butterfly function, now you do. All right, so it is the butterfly function. I also have like happy parabolas, sad parabolas. You got all kinds of things for me. So you'll catch up. You'll catch them as they go. Anyway, so this is a good old butterfly function, 1 over x. So we're integrating from 1 to 2. So somewhere over here is 1. And then we're going to 2. And we're looking at, what is this area right there? Right, that's what this is actually asking us to do. Now, you think about the definition using the sums, the Riemann sums. We could try to set it up that way, but it would probably be kind of rough. So instead, let's use the fundamental theorem of calculus. So what we need then is an antiderivative of 1 over x. So quiz for class. It's an antiderivative of 1 over x. What function gives us that as a derivative?
Actual log.
Good. Yeah,
Absolute
that's natural
value.
log. It's going to be the natural log of x. So we're going to evaluate the natural log of x at 1 and 2. And I apologize. I just noticed in the chat box, Devin, you asked for number 11. We might be able to get back to that. If not, for sure, I'll send you a message about it and we can chat about it, or you can come to office hour. Anyway, so the integral of 1 over x, the antiderivative of 1 over x is the natural log of x. So at this point now, we plug in our bounds. So we're going to get the natural log of 2 minus the natural log of 1. And the natural log of 1, hopefully you guys remember that. If you don't remember that, get to know it. The natural log of 1 is just 0. So our answer to this is the natural log of 2. So the area of that, the area under this graph between 1 and 2, is actually just the natural log of 2. It's like 0.69 something. All right, fast, easy, especially compared to Riemann sum. All right, here's another one. How about, let's look at the integral from 0 to pi over 2 of cosine x dx. So we'll throw a trig function at you now. All right, so we're going to go from 0 to pi over 2 cosine x dx. All right, so you all know what cosine looks like, hopefully. And so we're just going to see what do we get when we go from 0 to pi over 2. All right, well, again, we could do Riemann sums, but you don't want to do Riemann sums because you're going to have, you know, some sort of I over n inside of the cosine that then you're adding up. So instead, let's go to Fundamental Theorem of Calculus, right? It's a continuous function. We're good. That's all we needed, right? So if we go from 0 to pi over 2 cosine of x, we need an antiderivative of cosine. So what's the antiderivative of cosine? Give me a function whose derivative is cosine. All right, so a couple of you just threw in the chat box sine. Right? Do we use sine of x? Yeah, so this one's going to be sine of x. So Blake, you just put up negative sine of x. Negative sine is the derivative of cosine. But since we're going the other direction, we're looking for a function whose derivative was cosine. That's just plain old sine, right? The derivative of sine is cosine. And don't feel bad about that one. That mistake happens all the time. Sine and cosine do that to us because of the fact that the derivative of cosine is negative sine, derivative of sine is cosine. They're related to each other. So the plus or minus will probably bite you a couple times. But for cosine, its antiderivative is just sine. So this is going to be sine of x that we're going to evaluate at 0 and pi over 2. So this is going to be the sine of pi over 2 minus the sine of 0. All right, well, now we got to remember our trig. Uh-oh, got to remember our trig. Okay, sine of pi over 2. Anyone remember what that is? All right, good, that's 1. And then how about the sine of 0? That's 0. Good, thanks, Mariola. This is going to be 1 minus 0, which is 1. So the integral of cosine from 0 to pi over 2 is 1. Nice. It actually is really nice, because check this out. Draw the graph of cosine. So this guy, right? Cosine does this. And we're integrating from 0 to pi over 2. So 0 is right here. Pi over 2 is right there. And so integrating from 0 to pi over 2 is this little chunk right there. So check that out. The area of that little piece is 1. Whoa. All right, so for those of you who really know me and know I've got this like kind of weird obsession with the trig functions, this is another reason why. That's incredible that that area is just nice 1. So like in this hump, this total hump has an area of 2. Why in the world is it such a nice number, right? Why? Like you think about this one, it was the natural log of 2, which is still, I mean, a decent number, but it's not 2. It's not 1. So kind of interesting, but there you go. So we like the fundamental theorem of calculus, at least this portion of it, because it lets us do these integrals quickly. All we need is an antiderivative, right? So if it's a function where we can find the antiderivative, then the fundamental theorem of calculus makes this super quick and easy. And even if our function's not positive, right? If we've got a function that's below the x-axis, we'll still get the correct value for the integral. It will be negative, right? The negative signed area, or it will take the positive and subtract the negative pieces and all that. But the fundamental theorem of calculus always works. Like, let's take this one and let's just change it slightly. Instead of from 0 to pi over 2, let's go 0 to pi. So we'll integrate from 0 to pi cosine of x dx. Now this is really easy because we don't have to do anything differently. The antiderivative is still sine. We're now going to plug in 0 and pi. So this is going to be sine of pi minus sine of 0. Well, the sine of 0 we already saw was 0. And then the sine of pi, you remember, is also 0. So we get 0 minus 0 or 0. Now, what ended up happening here is we increased the region, or the interval over which we're integrating, from 0 to pi. Well, 0 to pi is now over here. So we're also getting this chunk that I kind of marked there in red. And what we know from the graph of cosine, since it's got all that nice symmetry, that area in red is exactly the same as the area in blue. So clearly my graph's not quite right, but technically those areas are the same. But remember what the integral does is gives us signed area. So it gives us positives when we're above the x-axis and negatives when we're below. So since these two are the same area, the blue one's going to be positive, the red one's going to be negative, they cancel each other out. And we get 0. Right? So this is beautiful. Always works. Always going to account for positive versus negative. We don't have to do anything anymore. You don't have to think anymore. All you have to do is get an antiderivative. Okay, so that's going to be our goal, is how do we get antiderivatives? But we'll get back to that. I need to show you the other part of the fundamental theorem of calculus, because this is the biggie. This kind of draws everything together. But before I go there, any questions on what I did just here? And if you'll indulge me for just a second, I'm going to see if I can get my computer back up. It just crashed on me, of course. So and then now I can't really see the chat window very well. So give me just one sec. You're going to get a real lovely view of me here in just a second. Ignore it. All right. Okay, so hopefully I'm good now. So let's look at the other part of the fundamental theorem of calculus. So this is the one that the book calls part 1, and I'm doing it as part 2. But here's the other part of the fundamental theorem of calculus. All right. So the other part of the fundamental theorem of calculus says this, that if you differentiate an integral okay, so we've got an integral here, f of t dt, and we're integrating from a to x. And if we differentiate that integral, we get f of x. Okay, so let me break this down for you a little bit, because as it is, you're probably like, whatever. So first of all, this guy a is a constant. So it's pick your favorite number, 0, 4, 300. All right, and then we're integrating from there to x of f of t dt. All right, well, what does that actually mean? Well, if we were to draw a graph of this, these axes now are t for our horizontal axis and y. So this is a ty plane, not an xy plane. We've got whatever our function is. Okay, so this is f of t. And we're integrating this from a to x. So on our graph, there is the place a, that constant that's fixed. And then we're integrating up to x. But x is a variable. Okay, x is a variable. It's going to change. So it could be a, it could be out here somewhere. But basically think of it as it slides. So as x slides, we're getting a different amount of area. As x gets bigger, at least in this picture, we're going to increase our area. So that thing that's in parentheses, like that entire thing that's in parentheses, that's the area in this picture. Okay, so that what I drew in green is this thing. Okay, so that's our area. And it depends on x. It's a function of x. If x is at a different place, we get a different area. So it's a function of x. But then what the fundamental theorem says, if we differentiate that function, that area function, we get the original function. Okay, so weird. But let me really like lay it out for you. So check out what happens here. We're taking a function, we're integrating it, then we're differentiating it. So when we do that in order, when we integrate and then differentiate, we get back to what we started. So integrating and differentiating cancel each other out. So do you remember what we call those things? Things that undo each other? The math term for that? Yeah, thanks, Blake. Those are inverses. They're inverse operations. So let's think about it. You've seen lots of pairs of inverse operations. Adding and subtracting. Those are inverse operations. Multiplying and dividing. Those are inverse operations. Squaring, taking a square root. Those are inverse operations. Well, guess what? Differentiating, integrating. They're inverse operations. So this is why these are lumped together in calculus. Because differentiation and integration are really the same thing. They're just two sides of the same thing. Right? Like logs and exponents, they're the same thing. just looking at it differently. So derivatives and integrals are really the same thing, just going in opposite directions. But if you look at how we apply it, like think about the Fundamental Theorem of Calculus part 2, the one that I showed you first. How do we actually do an integral? Well, we anti-differentiate. We do derivatives backwards because they're inverses. Okay, so this was actually huge. I know most of you probably don't care, but to mathematicians, especially at that time, this is back in the 1600s, right? This was mind-blowing that all of a sudden these two very different things are doing exactly the same thing, just backwards. I mean, even go back to the why do we do derivatives? What was the reason they did derivatives? Was to find slopes of tangent lines, right? Where did this definite integral stuff come from? Well, it came from looking at areas. So if you really think about it, what this is saying is finding areas under curves and finding slopes of curves of tangent lines. Yeah, it's really the same question, just on the opposite side. That really doesn't feel good. Why are they even remotely the same? Well, it's because integrals are adding things up, and derivatives are looking at how we're changing. So if what we're doing is we're adding up areas, we're changing our function, the rate at which it's changing is the rate at which we're adding up the area. So it actually does work. It does work if you really think about it, but it's kind of mind-blowing. That slopes of tangent lines and finding areas in their curves are really the same deal. All right, well, in terms of applicability of this, really all this is saying is if you differentiate an integral, you get what you started with. Okay? So, for example, this was one of the homework questions that I skipped over because we hadn't seen this yet. Well, now you're going to see how fast and easy this actually is. So let's actually look at, I forget which one this was, but it was, we're given a function, f of x is equal to the integral from 4 to x of 1/4 t squared minus 1 all raised to the 7th dt. All right, and then what it asks us to do is to find f prime of x. So we want the derivative of it. So here's some options. Here's what we could do. We could distribute this thing out. Take the 1/4 t squared minus 1 to the 7th, expand it out in a huge polynomial, then use the power rule to anti-differentiate each one of them, plug in 4, plug in x, get our number. All right, get our function. Then we can differentiate it using the power rule. So that's one option, but that's way too long. Instead, recognize we're doing exactly this. We're differentiating a function that looks exactly like that. All right, well, if we differentiate an integral, what we get is the same function that we started with. There you go. The derivative of this integral is just the function that was inside of it. I just changed the t to an x. That's it. Because derivatives undo integrals. Like, I swear, it really is this easy. Here's another one. Let's say we're looking at the derivative of the integral from 0 to x of t to the t dt. All right, well, I'm going from a constant to x. I'm going to differentiate with respect to x. So they undo each other. And what I'm left with is x to the x. And if you're feeling right now a little bit like you're getting cheated or like, wait, isn't there another step or shouldn't we be doing more? No, this is it. This is the beauty of the fundamental theorem of calculus, is that when we've got an integral of this form, differentiating it just cancels it out. All right, so that's all there is to it when you're in this form. But of course, sometimes you're not in this form. And this was another question, one of the homework questions that somebody wanted to look at. And it looked like this. We were taking a derivative of an integral from x to 14 of t cubed dt. And if you look at that one, that's pretty close to what our fundamental theorem of calculus looks like. But what's the difference here? Why can't we immediately use the fundamental theorem of calculus? All right, thanks, Blake. So the x is on the bottom, right? When we look at the fundamental theorem, it shows a at the bottom and x on the top. We don't have that. We now have our constant on top and x on the bottom. All right, so can we switch it? Can we make it so that it actually is an integral from 14 to x instead? Well, the answer to that is yes. Does anybody remember the rule? I showed it to you a couple days ago. But do you remember what happens when you swap the bounds? Cool, thanks, Alexi. Just put in the chat, she put in a minus. Right? This is actually the same as the negative integral from 14 to x of t cubed dt. So if you swap the bounds, you change the sign. Now that negative is a constant multiple, which means I can pull it out of the derivative. So we get a negative derivative of integral from 14 to x of t cubed dt. And now this guy's perfect. So what we're going to end up with then is a negative x cubed. So the t cubed just turns into an x cubed. And the minus sign got kept because of the fact that we swapped the order of integration. So sometimes you do have to fiddle with the integral a little bit to be able to actually do the fundamental theorem of calculus. But if you can get it into this form, integral from a to x of whatever, it's super fast and super easy. All right, so here's another variation. Here's another one that's related, but isn't quite the same. What if, instead of going to x, we went to, say, x squared? Right? So let's say we're looking at an integral from 2 to x squared of, let's say, sine of t dt. So if that wasn't an x squared, if it was just x, we're pretty much done. The answer would be sine of x. Okay, but it's an x squared. So it's probably real natural to think, okay, we're just going to plug x squared in. So we get sine of x squared. Okay, well, we're going to do that. But we also have to think about this. We have one more piece to this puzzle. Because of the fact that this is x squared, what we're really doing is function composition. Right? I'm putting another function, x squared, into this other function, the integral. All right, now, in the end, I'm differentiating it, right? What I'm going to do here is I'm going to differentiate this thing. I'm differentiating composition. So what's the rule for that? What rule do we use for differentiating composition? Good, chain rule. Thanks, Blake and Rigney. So this is chain rule. So do you remember how chain rule works? We differentiate the outer function, and then we multiply by the derivative of the inner function. So what this is going to look like then, the answer to this is going to be sine of x squared. That's the derivative of the integral. But then we need to multiply by the derivative of this function that we're putting in. So we're putting in x squared, we need its derivative, and its derivative was 2x. So the answer to this is 2x sine of x squared. So if your bound isn't just x, but it's some other function, just use the chain rule. Do the chain rule and you're good to go. So here's another example. Let's say we have the integral from 3 to tangent of x of, let's just say 3t plus 1 dt. And then we're going to differentiate that with respect to x. All right, so here's what we get. I'm going to substitute in the tangent of x, so I get 3 tangent of x plus 1. But then the chain rule says I need to multiply that by the derivative of tangent. So quiz for class, derivative of tangent. Uh-oh. Anyone remember the derivative of tangent? All right, I'm going to suggest, okay, thanks, Rigney, it is secant squared. Go back, look at all your derivative rules, because we're going to need them. Anti-differentiating all the time, we're going to want to go backwards. So make sure you go back and you refresh those. So this one is secant squared. All right, so the derivative of that, well, the derivative of the integral is just the stuff inside, evaluated at tangent, but because of chain rule, we have to multiply by secant squared. So hopefully you're getting the feel of how this works, but the key is that the derivative undoes the integral. They cancel each other out. All right, let me show you one more variation on this, because sometimes you'll run into this problem. We're going to keep doing this whole derivative of integral stuff, but this time, let's differentiate the integral from x to x cubed. And let's just put on the inside e to the t dt. All right, so what's weird about this one? Why am I bringing this up as a case? What's different about this guy than the other ones we've done so far? Yeah, there is dead on. There are two variables. There are bounds. Both of the bounds have x, right? As the Stephanie just put in there. Uh-oh. Now, if they were both just plain old x, the integral from x to x, this would have been easy. That answer would have been 0, right? Because the bounds are exactly the same. But this one's not. All right, so here's what we have to do. We have to split this up. So what we're going to do, we're going to do a d dx here. But I'm going to split it up into an integral from x to a e to the t dt plus the integral from a to x cubed of e to the t dt. So a is your favorite number that's between x and x cubed. All right, so basically I'm using that rule of integrals that says I can take any integral and split it into two pieces, right? We can think of this area as the area from x to a and then from a to x cubed. So I can split it into two. Now, what this allowed me, or the reason I did this is if you look at like the second integral, we're good now, right? We've got our constant bound on the bottom, and we can apply the chain rule and be done with it. This first one is not quite in a spot where we can use it yet. However, I do have my constant bound now. So this is the same thing that we did just a little bit ago where we just swapped the order of integration. So let me change that real quick. So we're going to do a d dx of negative integral from a to x e to the t dt plus integral from a to x cubed e to the t dt. So both of these integrals are now ready for me to use the fundamental theorem of calculus. So what we're going to get is a negative e to the x, just change that t to x, and I'm going to get plus e to the x cubed times the derivative of x cubed, which is 3x squared. All right, so these are just variations on the fundamental theorem of calculus. But the important piece, the important thing to recognize is that derivatives and integrals are just inverses of each other. They're inverse operations. They cancel each other out. So the area question and the slope of tangent line question are really two sides of the same coin. Weird. Totally. All right. So how are we feeling about the fundamental theorem of calculus? Yeah, not too bad. Hopefully, at least the part that we saw last time, hopefully you get the idea. It's just a matter of finding the antiderivative and plugging in the bounds. This one's a little bit rougher, but basically, it's just they cancel each other out. And yeah, Hava, I think you're right. It's going to take a little bit of practice with these. You do a few of them. I think you're going to start seeing how they work, and they will come easier as we go. All right, so fundamental theorem of calculus. Oh, by the way, there are other fundamental theorems. There's the fundamental theorem of algebra. That was the one that says if you've got a degree n polynomial, it's got n roots. So there's also a fundamental theorem of arithmetic. I don't remember which one that is, but there are some other fundamental theorems, some like core things. But this is the fundamental theorem of calculus, and it's the reason calculus even matters, right? Or how it really lets us do this integral idea much faster. All right, so it all comes down to antiderivatives. So we got to really practice and think about how do we find antiderivatives. So let me start by doing this. Let me give you some functions that we know how to differentiate. I'm going to just make a little list here to review. Because obviously if we know our derivatives, we're going to be able to do our antiderivatives. So I'm going to make a list here where I've got big f of x and little f of x. I'm specifically writing it this way because I want us to think integral-wise. We're starting with the right side and we're getting the left. But when we build it, we're just going to differentiate. So for example, power rule. I've got x to the n. Its derivative was n times x to the n minus 1. Right? So this was the power rule. Power rule said, bring your exponent out front as multiple, decrease the exponent by 1. So now when we anti-differentiate, we add 1 to the exponent, and we divide by that exponent. Right? Power rule. So any polynomial you can take care of. Some other function, and also it works for negative powers and roots and all that. So other functions to know. Natural log of x. Its derivative is 1 over x. So when we integrate 1 over x, we get natural log. How about e to the x? Anyone remember the derivative of e to the x? Yeah, this is the easy one that everybody starts throwing. It's just e to the x. So e to the x is like the best function ever. You differentiate it, you get e to the x. You integrate, you also get e to the x. All right, so then we have sine and cosine. So the derivative of sine was negative cosine, and the derivative of cosine was sine. So when we go backwards, recognize that sine just gives us cosine. But if we have just cosine, so I'm going to write that just right here. It's just plain old cosine of x. What we're going to get is negative sine of x. Because the minus would get distributed. So when you see cosine, its integral is going to be negative sine, but it comes directly from the derivative rule. All right, so there were sine and cosine. Let me just remind you about the others. Let's just look at tangent and secant, because cotangent and cosecant are just negatives of those. So we'll continue our list here of big F and little f. So tangent, its derivative was secant squared. So if you're given a secant squared, you can integrate that and get tangent. And then secant was secant times tangent.
Bruce?
Yes.
Derivative of sine x, isn't it cosine x, not negative cosine x?
Oh, you are right. Thank you. I had those backwards. Because I was, yeah. Thank you for catching that, Mariola. And I know exactly why I did that. Because I was thinking antiderivatives. All right, so derivative of sine is cosine, derivative of cosine is negative sine. So if we integrate sine, that gives us negative cosine. Sorry about that. All right, so let's see, we got our natural log, we got e, sine, cosine, tangent, secant. Another important one is inverse tangent. We also had inverse sine, inverse cosine, right? We had all those inverse functions as well. But I'll just tell you the inverse tangent is probably the most important when it comes to integration. So anybody remember its derivative? Beautiful, good job, Brittany. It's 1 over 1 plus x squared. So if we have the form 1 over 1 plus x squared, we anti-differentiate, we're going to get inverse tangent. All right, and this list goes on, right? We could do the generic exponential, we could do the generic logs, we could do all that. But these are some of the more important rules, ones that we're going to see more frequently when we need to anti-differentiate. So go back, practice them, remember them, and get good, or really where you need to practice is going from right to left, because you're probably pretty good with the differentiation direction. We now need to turn that around. So start on the right side of this chart and work on going to the left. All right, so we've got lots of functions that we can integrate. Right? We've got lots of things that we can do. However, there are others that we have to figure out. For example, what if I ask you to find the integral of, say, tangent of x? Or what's the integral of natural log of x? These are relatively nice functions. But the problem is we don't have anything that we know whose derivative is tangent. Yes, we know the derivative of tangent, but we don't know a function whose derivative is tangent. And the same thing with natural log. We know its derivative, but we don't know a function whose derivative is natural log. So what we're going to have to do is we're going to have to develop new techniques. We're going to have to figure out ways to find antiderivatives for these kind of functions. And that's what the next big portion of this class is going to be. Is we're going to be learning integration techniques. How do we find these antiderivatives? So the first one I want to show you is what we call substitution. All right, so let me just give you a list of some different techniques that we're going to run into. All right, so we're going to start today with substitution, but there are all kinds of other ones. There's integration by parts. There's trig substitution. There's partial fractions. And some others, but these are the big four we're going to learn. And each of these methods is used with certain forms of functions, depending upon what it looks like. We're going to use different things to help us get there. But we're going to start easy. We're going to start with substitution. And integration by substitution, this is done when our functions are pretty close to something we know how to integrate. Okay, they're actually really quite close. And we can turn them into a function we know how to integrate if we do a little bit of a substitution. All right, so let me show you what I mean with an example. So we're just going to start right in here with substitution. All right, so here you go. Nice and easy question. I want you to get an integral of e to the 2x dx. I'm not putting bounds on it, so this is an indefinite integral, which means we're only looking for an antiderivative. We're not plugging anything in, we just want an antiderivative. All right, so you see the e to the 2x, and you get a little bit excited. At least you should get a little bit excited because it's e. We like e to the x. But the problem is this isn't e to the x. It's e to the 2x. All right, so here's what we're going to do. I would much rather have it just be e to a variable, right? If it's e to the x, I know its integral is e to the x. E to the u, its integral is e to the u. E to the t, its integral is e to the t, right? If it's just a single variable up there, then its integral is just itself. So what I'm going to do is I'm going to substitute. And I'm going to go, I don't want a 2x up there. Instead, I would like to have just, say, a u. Because if I can make it so that 2x is equal to u. Then I'm going to have an integral of e to the u. And that I like. That's easy. Its integral is e to the u. All right, so basically, I'm just going to turn it into a form that I want. I know that feels wrong. I know it totally feels wrong. But, you know, mathematicians, we're kind of sore losers. We don't like being told we can't do something. So we invent stuff all the time. You're like, yeah, I'm just going to do it. It'll probably work out. As long as you follow the rules, it works out. Okay, but here's the deal. I need to change all of the x's into u's. I still have to take into account the fact that this was a dx. And I need to change that into something with a du. And here's the hard part of integration by substitution, is finding the way that we do that. But it's actually not that hard. It's just going to require us to do something we already know how to do. And that is, we're going to use our derivatives. So come back over here. I've got u equals 2x. What I'm going to do is I'm going to differentiate this. I'm going to differentiate this with respect to x. So on the left-hand side, I'm going to get du dx. That's the derivative of u with respect to x. But on the other side, when I differentiate 2x, I get 2. So I know what you're thinking, probably. Like, okay, so why do we do that? Well, can anybody answer that? Why did I do that? What does that let me do now? So it is u prime. Now another way of thinking about it. Well, here's why I did that. Remember what I'm trying to do? I'm trying to get rid of this dx. I can use this to solve for dx to plug it back in. So if I just do a little algebra on this, right, I get du is equal to 2 dx. Multiply both sides by dx. And then if I divide by 2, I get the dx is equal to du over 2. So that means in order to completely change my integral to this new variable, I have to change that dx as well into a du over 2. Okay, so we just did a lot of work here, but I want you to see where we ended up. And I intentionally changed the colors here. When it was originally in purple, I wasn't sure what to do. I don't know how to integrate e to the 2x. By changing it, using the substitution, I now have 1/2 e to the u du. I turned it into an integral that I know how to calculate. All right, so what's the integral of e to the u? What's the antiderivative of that? All right, good. It's e to the u. But don't forget, what else do we have to put in when it's an indefinite integral, when there are no bounds? It's our good old plus c. So we get 1/2 e to the u plus c. So this is 1/2 e to the u plus c. Since c is any arbitrary constant, dividing it by 2 still makes it arbitrary. Okay. Don't write 1/2 c. 1/2 c is still c. It's still an arbitrary constant. All right. So look at that. By doing a substitution, we turned it into a form that we were able to anti-differentiate. Okay, but There's always a but. But we're not done here. Because here's the deal. I started with x's. I need to end with x's. So I need to change this u. I need to go back and substitute. I know that u was 2x. So here is the antiderivative of e to the 2x. It's 1/2 e to the 2x plus c. So you're going to see me color code. Like I started with purple, I ended with purple. Purple was my X world. I always do that. So you'll be used to seeing that on the board here. But make sure you always get back to your original variable. All right, so this is the idea. This is what we're going to try to do. We're going to try to substitute, turn it into a form that we know how to antidifferentiate. We just have to make sure we replace all of the x's. All right, so before I show you another example, any questions on this one? All right, well then let's do another guy. Let's try this one. Let's integrate x times the sine of x squared minus 4 dx. All right, so here's the function that we're going to try to integrate. All right, well, let's think of a substitution. So looking at this, what do you want to turn into a u? What would make this most likely something we could integrate? All right, cool. A couple of you put it in there. How about u equals x squared minus 4? So I got that from Alexia and from Stephanie. Thank you for that. All right, well, let's see what happens. Let's try it out. Because worst case, we try that substitution and we realize it's not working, and we try something different, right? It's not like it's high risk. All right, so let's see what happens if we do that. So I'll let u equal x squared minus 4. Now, of course, that means that we need to replace the x and the dx as well. So let's get the dx first. And we're going to get that by differentiating. Now, I want to show you a little bit of a shortcut. So remember when I did this before, I differentiated both sides with respect to x, and then I did some algebra. I want you to key in on this step right here, what we got after we got rid of the fraction by moving the dx to the other side. And I want you to look at specifically where we started. So what we can do, notice that the du is the derivative of u, and the 2dx was the derivative of 2x. We can actually expedite this process by just doing this. The u, its derivative is going to be 2u. If I differentiate the other side, x squared minus 4 is going to give me 2x, and then times my differential, dx. If you go back to last quarter, go back and look in volume 1 of the calculus book, you'll see the section on differentials. We did this trick all the time. So we're going to save ourselves a little bit of time, a little bit of effort by jumping right in and just doing that. Okay, so this is what du is equal to. So let's solve this for dx. So dx is equal to du over 2x. So let's go ahead and put these things in. So now we're going to have the integral of x times sine of u times du over 2x. So looking at that, you still see x's. However, luckily enough, those x's are going to cancel. So once those are taken care of, we're left with 1/2 integral of sine of u. Cool. This we know how to integrate. We know the antiderivative of sine of u. So by changing it, it's now in a form that we can antidifferentiate. So this is going to give us a minus 1/2 cosine of u plus c. Right? It's negative because the derivative of cosine is negative sine, so we need that negative to cancel. But we still have the one last step we got to do, which is to get it back in terms of x's. So we'll replace that u. So we get minus 1/2 cosine of x squared minus 4 plus c. And so that, ladies and gentlemen, is our antiderivative of x sine of x squared minus 4. All right, so legit, the hardest part is figuring out what to substitute for so that you can actually calculate or get it into a form that you can actually do the antiderivative. All right, now these have been just indefinite integrals, no bounds or anything. What do you think changes when we have bounds? Like if I've got numbers on these integrals, what's going to change here? What do I do differently? What do I do the same? All right, so Susanna just says, plug it in and subtract. Yeah, there's one more step. That's the only difference. If I were to put bounds on here, like let's say this had been from 0 to pi, now that I'm at my antiderivative, I plug in 0, I plug in pi, and I take those numbers and I subtract. Right? So nothing changes with the bounds. There's just one more step that we have to do. So let me show you an example, just so you can see that it's not that big of a deal. Let's say we're going to integrate from 0 to 1, x cubed times x squared minus 1 to the 7th dx. Now, this one we don't have to do substitution. You could, again, distribute this thing out, right? Distribute it out, raise to the 7th power, multiply by x cubed, have that, whatever huge polynomial, do the power rule on each piece, plug in your numbers and be done, right? So we could do that. But instead, I'm going to show you why substitution might be a little bit nicer. So what do you think would be a good choice for our u? What do you want to let u equal here? All right, so Stephanie just said, how about x squared minus 1? Sounds like it's a good place to start, because if nothing else, that's just u to the 7th, which is going to be way easier, right? So let's try it. Let's let u equal x squared minus 1. So then du is going to equal 2x dx. So dx is equal to du over 2x. So let's plug all that stuff in and see what happens. So we now have bounds of, well, let's see, we've got x cubed times u to the 7th times du over 2x So this x that was down with the du is going to cancel with one of the x's there. So here's where we are once we substitute in for the stuff inside the parentheses and the dx. You should be not so happy right now. What about this integral is not so great? Yeah, there's two variables in here, right? Oh, where'd the 2 go? I just forgot it. You guys are awfully picky. But really the issue, other than the fact that I forgot the 2, is that we've got 2 variables still. And that's not okay, right? Remember what we're trying to do is get this only in terms of u. So I guess the question is, are we screwed? Was this a bad choice for our u? And don't worry, Stephanie, this is not a judgment on you, right? I definitely wanted that to be our u. But are we toast? Like really the question is, can we make x squared equal something in terms of u? All right, so I don't know if that no from Alexi is no, we can't do that, or no, we're not screwed. Because here's the answer, we're not done. We actually can replace that x squared. I want you to go back to look at the very beginning, what we chose for u. So let's come on back up here, way back up here. U is equal to x squared minus 1. Solve that for x squared. If I take this, I just add 1 to both sides. I get that x squared is actually equal to u plus 1. And if I put that in, now everything is in terms of u. And it's also not that bad to integrate, because if I distribute, I have u to the 8th plus u to the 7th. Both are really easy to integrate. So, Stephanie, good choice. Good choice for the u. It didn't seem like it, right? It looked like we ran into a problem. But this is a little trick that sometimes you need to play when you do substitution. Okay, just recognize that the original substitution, we've still got that. We can still use that to help us with any remaining x's. And in this case, it actually turns it into a really nice form to integrate. So let's finish this thing out. So we've got our 1/2. We're going to get u to the 9th over 9 plus u to the 8 over 8. All right. But now let's turn it back into x's. So if we go back in terms of x's, this is going to be 1/2 times u was x squared minus 1. So x squared minus 1 to the 9th over 9 plus x squared minus 1 to the 8th over 8. And since this was a definite integral, the last step, because remember before, when it was indefinite, we were done. We put a plus c and we were done. But now, because of the fact that this was a definite integral, I need to plug in the numbers 0 and 1. So that's what I was saying. There's just one extra step here. When we plug in 1, 1 squared minus 1 is 0. So all of this stuff is 0. When I plug in 0, I'm going to get negative 1 to the 9th over 9. So that's negative 1/9. This one I get negative 1 to the 8th over 8. So that's a positive 1/8. And I think that this ends up being minus 1 over 144. Definitely check my arithmetic on that. But I'm pretty sure it's negative 1 over 140. All right, so there's just that one last step. That one last step of putting in our bounds. But I want to show you a slight little shortcut. All right, this is a shortcut that I use because I find that this is actually more work than I need to do. I like to change the bounds when I change my variable. Right? Let me show you what I mean. So remember our substitution was u equals x squared minus 1. And I had two different x values, right? 0 and 1. So if I let x equal 1, I get u equals 1 squared minus 1, which is 0. When x is equal to 0, I get u equals 0 squared minus 1, which is negative 1. So when I change this from x's to u's, I actually can change my bounds on here to the u values, which in this case would be 0 on top and minus 1 on the bottom. Because negative 1 and 0 are the values for u when x is 0 and x is 1. Now, what that allows me to do is skip this substitution step. I still have this integral of u to the 8th plus u to the 7th, so I do that. But now I can immediately jump in and plug in my minus 1 and 0. I don't have to go back to x's. And you'll see that we get the same thing. Right? If I plug in 0, I get 0. And when I plug in minus 1, I get minus 1 to the 9th over 9. And minus 1 to the 8th over 8. Right? So notice that these are exactly the same thing. I just saved myself a substitution step. So that's Bruce's personal preference. This is what I do when I'm doing a definite integral with substitution, is I go ahead and change those bounds right away. Right? Because otherwise, you just kind of have to put placeholders here and be like, well, the bounds are going to change. I just don't know what they are. Right? So I put little stars here to remind me that there actually are bounds. but I got to substitute back in and blah, blah. Ugh. Why? Why? If you don't have to. It's a lot easier using your substitution just to plug in the numbers to find out what your new bounds are. All right, so that's pretty much the idea behind substitution. We will definitely do more of this because I see that we are out of time. So the plan for Friday. First of all, it is our first quiz, right? So our first quiz is going to happen. The quiz is going to open up on Canvas at 8:30 at the start of class time, right? Get in there, work on it. Make sure that it's uploaded by 9:10. So basically, I'm giving you a half hour for the quiz and 10 minutes to make sure you get it all uploaded and everything, right? So turn it into a PDF using your favorite device. Upload it. If you can't turn it in PDF, photos are fine. If you have trouble uploading it, send me an email, right? As long as the email has a timestamp, 9:10 or earlier, it's just as good to me. All right. So if you're having problems, send it to me in an email, but I'd much rather it go up through Canvas because it makes things a lot more seamless for me on my end. All right. So you're going to get in, do the quiz, and then come to class. Come to the Zoom room at 9:10. I'll be here. I'll be in the Zoom room so that if you have questions on the quiz or stuff pops up, I will be in here. But starting at 9:10, we will move on and we'll continue talking about substitution and basically keep marching on this idea of what integration actually does. So the quiz is going to cover the first 3 sections, so 1.1 through 1.3. So that's the integral ideas, the Riemann sums stuff, right? So the area approximation and the fundamental theorem. All right. So if I don't specifically say, feel free to use the fundamental theorem. But if I specifically say, hey, for this integral, create a Riemann sum, blah, 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 make sure you do it that way. You can use the fundamental theorem to check it, but make sure you do what I ask you to do. But if I don't specifically state, and it's just that here's an integral, feel free just to use the fundamental theorem. All right, totally cool. Anyway, so quiz Friday, 1.1 through 1.3 opens at 8:30. Make sure you grab it, do it, get it uploaded by 9:10, and then back into the Zoom classroom for class. Okay, so that's our plan for Friday. Any questions before I pause the recording? All right.